We also have 2 hours of class time that I need to actually post on the course page. So that will be coming before the weekend is out, because we want to make sure that we cover the content and also account for our contact time. Now, in addition to that, I'm checking the calendar and I am noticing this is the completion of week 7, I believe it is. So what that means is that when we come back from semester break, we are going to be pretty much starting the latter half of the course, and that's about what, another 7 weeks, if that. I'm not thinking it's 7 weeks, it's about just under 7, maybe 6 weeks of teaching time. So look out for your second test between the end of the week when we come back from semester break, either the end of that week or the beginning of the following week. Okay, I will show, of course I'll announce it, you will know in advance, but you also must be prepared for practice quizzes, and there will be at least one quiz that will be marked in between the semester break, when we come back from semester break, not the semester break itself, but that week after. There will be at least one quiz that you will be marked on. There may be more, but at least one. So just be on the lookout for that, and be on alert. Okay, so let us begin.
Dr.
As you
Hula,
guys know,
before you go,
yes,
assignments. Will you be giving any assignments? I noticed there were 2 assignments, but I don't see anything posted or mentioned thus far.
yes, you will be getting an assignment. I actually was waiting for us to come back from semester break to do that, because I wanted to make sure that there were some bases that were covered as it pertains to reaction mechanism and electron pushing and so forth. So since we've had that conversation and since we've begun it, we're in a position now to do the assignments that I want you guys to do. So I can say to you now that one of the first assignments, you will have two presentations actually. That's what your assignments will be. And actually your presentation will be along the line of making a chemical model. So the model of a chemical compound, an organic compound. So there will be more details along that line. I will post it on the page with an example, the course page, with an example of what I am asking you to do, so that you have an idea of what it is that you will be expected, or what will be expected from you. Yeah, but that's what I can say about it for now. I can't give details in terms of the rubric and what you will be marked on and those types of things. But expect that when we return from semester break. I'm trying not to give you guys things to do over your semester break, because it's supposed to be a break. So your first assignment will be that. Is that clear? Or is that enough? Sufficient answer to your question, I hope? I see a question in the chat here. Oh, thank you, Tom Shore. All right. Well, just know that this course will require you to work for your grade, definitely, because it's pretty demanding, and it will become more demanding as we go. Anyway, guys, let's get started so we can maximize this time. Okay, guys. So, once again, turning off video. All right, so we were talking about SN2, the conditions for SN2, right? And we know that our SN2 conditions have this particular sequence of electrophiles. So we have the methyl electrophile, which is the best. Then we have our primary electrophiles. And then we have the secondary electrophiles, and of course, finally, the tertiary. Now, as you can see here, the tertiary electrophiles have associated with it a big note, which is to suggest to you that the SN2 reaction does not happen with tertiary electrophiles. I do need to put a little caveat here and say that it's not that it doesn't happen, but instead it is that it happens very slowly. So here we are going to continue our conversation because it's important for you now to see what the other possibilities are where substitution reactions are concerned. To close off the topic of SN2, there's so much more that can be said, and I'm sure as you are reading you are encountering that, but we are not going to spend all of our time talking about SN2 reactions. Here it is that we see that for SN2 reactions, the leaving groups tend to be poor, weak bases, right? We know what governs a poor base, and we've already discussed that, so you already have an idea of what we are talking about. Our preferred solvents for SN2 reactions are nonpolar solvents or polar aprotic solvents. Now, let's take a moment and say why we are talking about this. At this point, you are familiar with the polarity, the parameters that govern polarity of a molecule. We know when a molecule is considered polar versus when it's considered nonpolar. And in the case of the SN2 reaction, the reason why the SN2 reaction would prefer this class of solvents is because this class of solvents are the solvents that are most likely to stabilize the intermediates or the intermediary species that exist within the actual reaction medium. It's important for you to know that in a reaction, there are many things that are happening at once. And so how your reaction may be ready to occur in terms of the reactants, but stability can be an issue if the reaction is being conducted in the wrong quote-unquote solvent. So if the solvent is compatible with the reaction process, then the likelihood of the reaction occurring more smoothly would be a higher chance. All of these things play a role in the activation barriers that we talk about so much when we speak about reactions. Okay, so it's not just the orbital interactions that play a role in terms of energy, but also stability that can happen within the environment of the reaction itself. And those types of parameters are contributed heavily by your solvent, the presence of a catalyst, the presence of temperature, and other variables. So this is one of the reasons why you would have been introduced to theories and ideas and principles such as Le Chatelier's principles and so on, because these help you to understand all the variables that are actually at play when a reaction is going on. Having said that, we are now in a position to go further with the SN2 reaction. Sorry, SN1, what am I saying? So, in our conversation today, at least in this lecture, it is the hope to actually be able to speak on the SN1 reaction mechanism, the reaction conditions, nucleophiles, electrophiles, solvent, and biological SN1 reactions. So what is the SN1 reaction? Of course, by now you're familiar with the term S, N, and the number. You know what these represent. In this case, the S will continue to represent the substitution process, N nucleophilic, and 1 represents the actual number of components that are participating in our transition state for the rate determining step. That's a mouthful, but I'll repeat it again. SN1 is what we would refer to as a unimolecular substitution reaction. And the reason it is referred to as unimolecular is because that is the nature of the transition state or the intermediate that is present in the rate determining step. So the rate determining step is the focus of our reaction. We know that our reaction comprises sometimes one or more steps, and if it does contain more than one step, then our focus would then be on the rate determining step, because that is an indicator of the activation barrier to the actual reaction process being successful. So in the case of the SN1 reaction, our rate determining step entails the formation of an intermediate that is unimolecular. And that unimolecular intermediate emerges from a unimolecular transition state. The reaction is a stepwise non-concerted mechanism. It has two steps, unlike the SN2, which had one step, and it is non-stereospecific, meaning it leads to a racemic mixture of chiral products. The term racemic or racemic actually is defined as an equal mixture of R and S enantiomers, or I should say an equal mixture of enantiomers. So the first step is considered the rate determining step, and this is the step that leads to our intermediate formation. It is the slow step, and this is where actually once this step is accomplished, we're able now to go straight and actually very quickly so into our second step, which is a fast step that leads to our substitution product. So here, our picture shows us that we have our nucleophile as before, our electrophile, and then we have our resulting substitution product in addition to our leaving group. We already know what we expect here is that the nucleophile will do what nucleophiles do, and the leaving group will do what leaving groups do. And overall, our electrophile is expected to receive the electrons from the nucleophile. So, our step one actually starts with our electrophile. The actual presence of our polarized bond in the electrophile itself between the electrophilic atom and the leaving group is really the center of reactivity. So our step one gives us an opportunity to zoom in on that bond because that's where the action is happening. Now, when you consider that bond, what we're seeing is that there is steric bulk and a polarized electronic bond between the electrophilic atom and our leaving group itself. These and other parameters are what govern the actual prompting of this first step to occur in the first place. So, as it is, that bond breaks and the electrons go to the leaving group. And when the electrons go to the leaving group does what leaving groups do and it leaves. Once the leaving group leaves, it takes its electrons away with it. But what that does is it leads to the formation of an unstable intermediate in the form of what we call a carbocation. Now we know that there are two types of ions in chemistry. There are anions and there are cations. Anions are negatively charged. Cations are positively charged. So our cation in this case is referred to as a carbocation, and that's because the carbon atom that once was bonded to our leaving group is now void of those electrons and is now a cation. This intermediate is highly unstable, as you could imagine, and that has to do with the fact that it is electron deficient. So of course, oops, I kind of jumped the gun there. Of course, in cases where the leaving group is a solvent molecule, then what we have is a process called solvolysis. And in this case, we see an example of that. So all we've done here is we've simply replaced X with S to represent the name solvent. And as a result of that, same process occurs, except that now you have your solvent molecule as the leaving group with the charge that is being born. Sometimes our leaving group will actually have a charge associated with it, and sometimes it will not. As we delve further into SN1 substitutions, we will see where that occurs and where it does not occur. But you can imagine that if this were, for example, a water molecule, then the charge would not be present. In fact, it would be a neutral byproduct. So once our carbocation species has been formed, the immediate step to follow would be rapid attack by the nucleophile. So notice this is an interesting difference between the SN1 and the SN2, in that the SN2 reaction starts off with attack by the nucleophile, and here the SN1 reaction is not starting off with the nucleophile. Instead, it is starting off with the electrophile. So here our carbocation intermediate is formed, and it is immediately attacked by the nucleophile, and that leads to our product formation. And of course, corresponding byproducts. So what is a carbocation? We already said, we've described to you that a carbocation is a positively charged carbon ion. Now this species is very electron deficient and highly unstable, and as a result of that, its formation is going to require an uphill climb in energy in order to be able to access this unimolecular transition state that must precede formation of the carbocation. So that's already giving you an energy picture or a thermodynamics picture as it pertains to what to expect, right, in your reaction profile. To access this intermediate, you can see that first of all, you have your electrophile, and it is as normal as one would expect, a neutral molecule. But in the process of going from the electrophile to our carbocation intermediate, we have to proceed by way of a transition state. And this transition state is one where the bond is not fully formed and neither is it fully broken. So that is what we'll be here to explain, or that's what explains the presence of the dashed bond here, where once was a solid bond. As you proceed here, of course, if we look at these three species, we can imagine that in terms of energy, this molecule here, which would be the starting electrophile, is expected to be the most stable of the three. So you'd have most stable, least stable, and then intermediate stability. Of course, once you get to this point, the carbon is not a happy camper, and so it's definitely going to be proceeding further towards completion in terms of reactivity. So more about our carbocation species, we want to see more about it in terms of its electronics and in terms of its sterics. And so here we have another picture of the carbocation. We know it's positively charged, but let's look at it in terms of hybridization and structure. So the intermediate carbocation is one that has trigonal planar geometry. You have been introduced to this geometry a number of times in this course and previously, and so you're familiar with it by now. We know that trigonal planar geometry means that there are, first of all, three substituents, and in this case the substituents are represented by methyl groups. And then we also know that those three substituents are equally displaced in a two-dimensional plane. So our two-dimensional plane here is what we would call our XY axis. And so here we can see that these bond angles are actually equally distributed in a 360 plane, or a 360 displacement, right? So we can have 120 degrees each, and pretty much that's it. Now your p orbital is in a perpendicular plane, and it is equidistant from both sides or both faces of the equatorial plane. And so our p orbital is not interfacing in any way with these substituents, neither is it interfacing with the orbitals of these substituents. But more significantly, our p orbital is empty. It doesn't have any electrons in it, and that's what would distinguish this carbon from an alkene carbon, because an alkene carbon would be one that has an electron inside the p orbital, and that's where your parallel pi bonds would be formed. In any case, hybridization is the same, sp2, and what makes this one different is that you see the electron deficiency resulting from the fact that there are no electrons in that p orbital. So in other words, our carbon has access to 2 electrons here, 2 electrons here, 2 electrons there. But as you can see, that only adds up to 6 electrons, which then means that it doesn't have a full octet. Okay, I want to clear that. Right, so our p orbital being empty leads to actually a carbon that is so electron deficient that it actually forces the molecule, I shouldn't say molecule, but the intermediate, to bear a formal charge of +1. All right, now that +1 charge leads to a hunger for electrons that has to be quickly satiated, and that's where the instability results from. Our nucleophile then is easy, has an easy job to do, which is to satisfy that deficiency. And so the driving force for the second step is already inherent in the instability that is present in that carbocation species. Because this carbocation is so electron deficient, it really does not matter what the strength of your nucleophile is, because the reality is that as long as the entity has electrons on it, this carbocation is prepared to do whatever is needed to receive those electrons. So then, as a result of that, the nucleophile can come and do what it does, and in this case we are seeing that it has the capacity to attack from either side. So that's one of the other things to note about a carbocation. It it is actually a planar molecule, not molecule, but a planar intermediary species that allows for attack to occur from both faces. So if we were to actually depict this, what we would see is our attack can happen in such a way whereby the nucleophile can approach either from the top or from the bottom. And of course, depending on the direction of its approach, that would lead to a different configuration in terms of stereochemistry. That's what's being depicted here, as you can see. One other thing to say at this point is that there is no hindrance or no preference as it pertains to direction from which the nucleophile can attack. Both angles of approach or both directions of approach have equal probability of happening. So the nucleophile attacking from the top is equal in probability as it attacking from the bottom. And that's the reason why our resulting products are equal in terms of product mixtures. Just 1 second. Right. So if we take a look then at some results, let's consider a reaction whereby we have an attack by a water molecule on a secondary, well, in this case, it's not a secondary, it's a tertiary electrophile. So we have our carbon here. The configuration is S. This is our leaving group. And of course, we have our two R groups, and they're different. So we know that this is a chiral molecule. To start our reaction, the first step that needs to occur is the loss of the leaving group. And so the way we will depict that is through our electron pushing arrow. So here, we're breaking that carbon-chlorine bond, and we're going to form our carbocation intermediate. And so we have the methyl group going up. We have the ethyl group coming down. And then we have a propyl group. And of course, here is our charge. Cl minus has been lost because when the chlorine left, it already had electrons surrounding it. It had 3 pairs of electrons surrounding it, and when it left, it took the additional 2 pair from the carbon-chlorine bond. So that gave it 4 pairs of electrons, essentially a full octet, and a formal charge of -1. Our carbocation intermediate is now ready and unstable enough for attack by the nucleophile. Now here our nucleophile is a water molecule. We have 2 of them. This water molecule has 2 lone pair electrons, 2 pairs of electrons actually on the oxygen atom. And so what we have is a quick attack onto your carbocation intermediate. So that then leads us to another intermediate, because we will see once I draw out the product what the result is. We have an attack by one of the pairs of electrons on the water molecule itself. And so we have to be mindful of drawing out our electrons. There is a hydrogen, there's another one, and there is that single lone pair. So we use this lone pair to do the attacking, and that would then leave this lone pair behind, which is what we have drawn here. All right, so when we look at this step, once we've done a step in our reaction mechanism, we have to check to make sure, we have to do an analysis to ensure that everything is in order and to see if we have accomplished what our initial objectives were. As you can see, the SN1 reaction has a little bit more complexity than the SN2 in terms of mechanism. All right, so our carbon, which was electron deficient, is now electron sufficient. We started off with 3 bonds and a positive charge. Now we have 1, 2, 3, 4 bonds. And if we check, we can see that the formal charge on our carbon has now gone to 0. It has gone from +1 to 0. Now the way to check that, you would have had that as part of your first worksheet, I believe. But just to recap, formal charge is equal to group number minus number of bonds minus number of lone pair electrons. So in this case, carbon is in the group number 4. Number of bonds, Right, it's in group 4 and it has 4 bonds. So it has a formal charge of 0. Let me change the color there. All right, so let's check oxygen, formal charge wise. Now oxygen came to us as a neutral molecule, as a neutral atom. So here in water, we have 2 pairs of electrons, and the formal charge of the oxygen, let's see, group number is 6 minus the number of bonds, 2, minus the number of lone pair electrons, 4. Formal charge is 0 when it is in water. Here now, when we're looking at this intermediate species, we can see that the formal charge is going to change, and our job is to find out what it now is. So here we are seeing that oxygen is group 6, number of bonds 1, 2, 3, number of lone pair electrons 2, formal charge +1. When we have a formal charge of +1, we do not write the 1. Okay, it's understood. And for that reason, that's why you see we have the plus sign with a circle around it. That's pretty much an indication that it's a plus charge of 1. Okay. Let me just tidy this up. So right. Good. So we've seen now what our formal charge is for the oxygen. And the rule of thumb in writing out a mechanism is that once you have charged species, your reaction mechanism is not complete. So we are at a stage where we've done step 1. Here, we've done step 2. So the first step was the leaving group loss. The second step was nucleophilic attack. And now, because our product is a charged species, we have to tidy that up. And so the way we will tidy that up is by way of, in this case, it would be an acid-base reaction. So here you can see that this part of the molecule, so we've addressed carbon, carbon is fine, it's now substituted and it's neutral. It has the four bonds around it. So it's no longer electron deficient, it's okay. However, oxygen is not okay. Oxygen is part of a charged species, and that's not going to remain, that's not a stopping point or a sufficient enough place of stability in terms of energy for the reaction to stop. So what that then means is there is a driving force for further reactivity, because oxygen does not like to carry a positive charge. It's an electronegative atom, and so it is inclined to be neutral, and so that's where it's going to go. That's the intention or the driving force here in this reaction. So when you look at this species that I've highlighted here, you can see that this looks similar to a hydronium species, where you have H3O+. And we know that when we see these, we are immediately remembering, we can easily remember the acid-base reaction. So if we have, as you can remember by now, we had two equivalents of water, and we know that water can play the role of being acidic and basic when necessary. So in this case, we need that additional water molecule to behave like a base. And of course, if it does that, it can deprotonate. So what I've written in red is just an example, but we're actually going to now do this on the actual molecule itself. So here is our water molecule that is going to attack our hydronium type species. And note my electron pushing. The arrow starts at the electron and ends at the actual element. Source to sink. So when it attacks the hydrogen bond, it will push electrons from the OH bond back onto the oxygen. And that's how we are able to get our final product, which in this case is a CH3 and this is our tertiary alcohol. All right. Of course, byproducts. We will have byproducts that emerge from this part. So here is an H3O plus resulting from this attack, this deprotonation that occurred here. Plus, we have our Cl minus from the inception. So here it is. And so essentially this will dissociate and enter into an acid-base equilibrium to give us H2O plus HCl as byproducts in this reaction. Okay, let me know if you guys have any questions about that. That's the SN1 mechanism, and in this particular case it is one where we had actually 3 steps, but the substitution step, or I should say the SN1 steps, are step 1 and step 2, and then the final step was an acid-base reaction step. Okay, good. So of course you can feel free to put any questions in the chat if you have any as we are continuing on. At this time it is 10 minutes past the hour, so I'm going to make this my last slide. As you can see on the screen, we have a picture of an SN1 mechanism happening in a biological system. And this is actually a part of nucleotide synthesis. So what you see here is the initial cleavage of the carbon-oxygen bond. Now here is our leaving group. Let me draw that better. Our leaving group that's being stabilized by some magnesium ions. And our leaving group in this case is a phosphate anhydride. Of course, we have an anomeric carbon here in this pyran. And if we pay keen attention to our oxygen atom, it has 2 pairs of electrons. And so what we're going to have is an intermediate carbocation. I hope you can see that clearly, but that's the result. Now this carbocation is actually pretty stabilized. It's stabilized by the heavy partial negative charge that's present on this oxygen. So here we have that. Our carbocation has formed, and here is the resonance structure that permits the stabilization that I was referring to just now. Having attacked, having actually disconnected from the leaving group, we are now in a position to attack by the nucleophile, and here is the nitrogen in the ammonia that is able to do that. And of course, having done that, here is our product. Now, as we know, SN1 reactions are not stereospecific, but in living systems, once again, the rules can be broken. So what we see here is only one stereoisomer is being formed. All right, so I can stop at this time and I'll take questions if there are any. Katarzyna, you have a question?
Yes, Miss, I had up my hand since the slide before. Miss, I was about to ask you to please clarify for me one more time how the water
Uh-huh.
molecule acts as a base to push back the electrons onto oxygen on the bond.
In the previous one. Okay, I can do that. Yeah, I don't know why I didn't see your hand. Sorry about that. Oh, now I'm able to see it better. Okay, so let me go back. Guys, if you need to leave for any reason, that's fine. I'll just stay on with whoever it is that has questions at this time. So let's take, right, so this is where we were, right? So first, we've lost our leaving group. So let's just make it such that we'll call this R1, R2, and R3. R1, R2, R3. So that's the positive charge that results. Once that leaves, once that chlorine leaves, we get our carbocation and our water molecule. There are two of them. So make sure we put in our lone pairs. We can attack. We did that. All right, so you're okay with the formal charge calculation, yes?
Yes, Miss.
Okay, good. So we have this lone pair. Now, all right, so here we have an unstable. So this is unstable intermediate. Number one, unstable intermediate, number two. And so in order for us now to make this stable, we have to neutralize. Now to neutralize this, as you can see, this species here, like I was saying, looks similar to a hydronium species. And we know that a hydronium species is basically an acid. It's an acid species, an acidic species. Now, the way how that acidic species behaves is such that it's a proton donor. A base can come in, any base, as long as it's strong enough, and it can actually attack that proton. And if it does that, then the electrons from the oxygen hydrogen bond will break, causing it will break, causing the following to result. So we have OH2 and we now have that plus BH. So this is our acid base reaction. Yes. Um, does this make sense so far, Katarzyna?
Yeah, Miss, I'm following you.
Okay. I see a question from who am I talking to? Oh, Anuradha. Anuradha, I'm gonna pay more attention to the lab. I haven't looked at it yet, so I really can't speak to that at this moment. But once I get a chance to look at it, I will be able to open it so that you guys can see where your mistakes were. All right? Yeah, so Katarzana, what I'm saying here is that this is an analogy we're making. This reaction that I have on the top here is an analogy that is being made to this at the bottom. So essentially, this is how your acid-base reactions occur all the time. You're welcome, Anuradha. This is how your acid-base reactions occur all the time. Your base, if you have an acid that is water-based, or anything actually, your base will come as an electron-rich species and it will attack the proton on your acid. And when it does that, it forces the proton atom bond to break. I said proton atom bond deliberately because I don't want to, sometimes your acid it could be ammonia. Sometimes it could be a whole host of other things. But whatever the acid is, it's the same mechanism. Anyway, so here we are. In this case, our second water molecule is behaving as a base, and your unstable intermediate number 2 is behaving like an acid. And when it takes on these roles, it is doing the same thing that is done up here. Attack, deprotonate, leading to the product where you have neutralized species R1, R2, R3, plus H3O, and then Cl minus from over here. Does that make sense? Is that okay?
Yeah, miss, I understand. So when the water molecule attack the proton, right, miss? Miss,
Yeah.
the proton comes off of the molecule, right? It becomes neutral after that, correct?
Yes. And this is what you form here.
Okay, I understand.
Right. And so here, you see this part in the product. This is what, when they show us this, what they're saying is you can get equal amount of S and R because the attack on the carbocation, the attack on this carbocation is from the top, 50% from the top, 50% from the bottom.
So they're like enantiomers, right, miss, as you mentioned earlier, because they come from, okay, I understand. Because of how the molecule is, they can attack from either side. And on a mirror image, it would be the same thing, right?
That's right. So it's equal components, 50% each. 50 to 50. 50 S, 50% S here, 50% R here. Yep. Good question. Thank you for asking that. Anybody else? All right, good. So you guys are in a good place to do the worksheet. And I will post the other two recordings, and so you will use that to tighten up. All right, Jiram, you have a question? What's up?
Good day, Miss. I have a question with regards to Chem Lab. Are you
Uh-huh.
at capacity right now? Um,
Am I?
with the grades, right? Is there any way I could get like a review to see where I got wrong?
Yeah, once I haven't gone through it yet, so once I do that, I'll be able to open it up so you guys can see.
So the grade that is shown on Moodle isn't ideal, isn't finished.
It's not final because I have not looked at it yet myself. The grade that is on Moodle is the automated grade, right? But because the questions were short, there were some short answer questions on there. Some of those short answer questions would have had some, I wouldn't want to say errors in marking, but because of the way how the software marks, it's very restrictive. So if you put a capital letter, or if you put a full stop, or if you put a comma, it might actually have marked it wrong when it should not have. So I have to make sure I go in and see before I actually publish those grades as final. You understand?
All right, Miss. Thanks, because I wrote some of my short answer questions as full sentences rather than one
Okay.
word. Yeah.
Yeah, it doesn't give you the option to just like I guess I have to search it, but I don't see the option to just make the answer based on keywords, because if it did, then it would give you guys more scope to, like be flexible in how you articulate it. So for example, one of the answers would have been phenyl. It may have been phenyl carboxylic acid and ester, I think. But if it was spelt wrong, then you would get it wrong. If it was spelt with a capital letter or something like that, then Moodle might have marked it wrong. So I have to check.
All right, Miss. Thanks.
Yeah, you're welcome. I'm gonna stop this recording now.